SwayamPrabha. Digital India. Educated India.
Advanced Technology for Textile Wastewater Treatment. Lecture number 18. Advanced technology for textile wastewater treatment. It is a very critical issue due to the significant amount of pollutants it contains, such as dyes, heavy metals and organic compounds. In the previous lecture, we looked at the analysis of these in great detail. Advanced technology plays a crucial role in addressing these challenges. Here are some advanced technologies used in textile wastewater treatment, and this we have learnt in the past, but we will look into it in a little more detail as a dedicated lecture for these advanced technologies. Membrane filtration. Membrane processes like ultrafiltration UF, nanofiltration NF and reverse osmosis RO are effective in removing suspended solids, dyes and other pollutants from textile wastewater by using semi-permeable membranes, and these membranes are of different porosity. Advanced oxidation processes AOS. AOS like ozone treatment, Fenton reaction and photocatalysis using materials like titanium dioxide and zinc oxide are highly efficient in degrading organic pollutants, dyes and other recalcitrant compounds present in the textile wastewater. Activated carbon adsorption. We have learned this, but we will see this in more detail. How does it work? What is the functionality? Activated carbon is effective in adsorbing organic compounds, colorants and odorous substances from textile wastewater due to its high surface area and porosity. The porous part in the activated carbon helps in the adsorption. Biological treatment. Advanced biological treatment processes such as sequencing batch reactor, that is SBRs, membrane bioreactors MBRs and constructed wetlands utilize microorganisms to biodegrade organic pollutants and remove nutrients from textile wastewater. Electrocoagulation. Electrocoagulation involves the use of electric current to destabilize and aggregate suspended particles, colloids and organic compounds in textile wastewater, facilitating their removal through sedimentation or filtration. And all of this we have studied in the past, but we will look at it in more details in this lecture. Forward osmosis. Forward osmosis or FO is a promising technology that uses a semi-permeable membrane to draw water through osmotic pressure, leaving behind contaminants in textile wastewater. It is energy efficient and suitable for concentrating pollutants for further treatment or resource recovery. So, at this stage, either it is done for making the effluent a little better and purer by removing some of these, and it is also beneficial that at this stage some recoveries of useful compounds can be done. Membrane distillation. Membrane distillation or MD is thermally driven separation process that utilizes hydrophobic membranes to separate water from contaminants in textile wastewater based on vapor pressure differences. It is particularly useful for treating wastewater with high salinity or complex composition. So, each one you will see has its own role to play. These technologies are all advanced technologies, let me repeat once again, and they have been devised based on the fact that there was a need for such a technology, because when the wastewater could not be treated for a particular parameter effectively, the scientists and researchers felt that they should find a better method, and that is how the science advances. If we think that this is it, now nothing much can be done beyond this, that is not what is science. Science is a continuous process where more and more innovative technologies are brought to the industry, so that the industry eventually gets benefited. Sonochemical treatment. Ultrasonic waves can be applied to textile wastewater to induce cavitation, generating highly reactive hydroxyl radicals that degrade and organic pollutants and enhance the effectiveness of other treatment processes. So, that was a new method which we did not discuss earlier, sonochemical activation. Microbial fuel cell, MFC. MFCs utilize microbial activity to generate electricity while simultaneously treating textile wastewater, offering a sustainable approach for both energy production and wastewater treatment. Advanced monitoring and control system. Integration of advanced sensors, real-time monitoring and control systems can optimize the efficiency and performance of textile wastewater treatment processes, allowing for proactive management and resource optimization. So, if we are able to monitor and control the system, and by integrating advanced sensors, real-time monitoring, control systems, we can optimize the efficiency and performance of these processes and treatment processes particularly. Combining multiple advanced technologies in an integrated treatment approach can provide comprehensive solution for the efficient and sustainable treatment of textile wastewater, helping to mitigate environmental pollution and conserve water resources. Phenton oxidation of textile effluent. We have been talking about this term. Let us now see what exactly is phenton oxidation and how does it work on the textile effluent. Phenton oxidation is a powerful advanced oxidation process under the category of advanced oxidation processes that involves the generation of highly reactive hydroxyl radical through the reaction between hydrogen peroxide and ferrous ions. This process is widely used for the treatment of various industrial wastewater, including textile effluent, due to its effectiveness in the degradation of organic pollutants, colorants and other recalcitrant compounds. In the context of textile effluent treatment, phenton oxidation offers several advantages. Degradation of organic pollutant. Textile effluent contains a wide range of organic pollutants, and this we know, we have learnt it time and again, including dyes, solvents and other chemicals used in the textile manufacturing processes. Many of the auxiliaries, the surfactants, the emulsifiers, they are all organic pollutants, including dyes. Phenton oxidation efficiently breaks down these organic compounds into simpler and less harmful byproducts through hydroxyl radical attack. So, basically here also there is a generation of hydroxyl radical. A radical is far more reactive than an ion. Color removal. Dyes are one of the major pollutants in textile effluents, contributing to water pollution and aesthetic issues in receiving water bodies. Phenton oxidation can effectively degrade and decolorize the dyes, leading to a significant reduction in the color of the effluent. Minimization of sludge production. Unlike conventional treatment method such as biological processes, phenton oxidation typically generates less sludge, as it promotes the mineralization of organic pollutants into carbon dioxide, water and inorganic compounds. So, here also if there is less sludge produced by a method as compared to another method which creates more sludge, the second one is less preferred than the first one, and that is what phenton oxidation does. According to the literature and the information, biological processes create more sludge. Rapid treatment. Phenton oxidation is known to be relatively fast, having reaction kinetics which are very fast, allowing for rapid treatment of textile effluent streams within a short retention time. Now, this is time saving as well. Versatility. Phenton oxidation can be applied to treat a wide range of textile effluent regardless of their composition or complexity. It is effective in both batch and continuous processes. So, phenton oxidation is not only fast, but it works both on batch and continuous processes. However, when we have advantages for a particular method, there are bound to be some disadvantages and challenges, and so does the phenton oxidation also has. There are also some consideration and challenges associated with phenton oxidation in textile effluent treatment. Optimization of operating conditions. The efficiency of phenton oxidation depends on various factors such as pH, hydrogen peroxide and ferrous ion dosage, reaction time and temperature. Optimizing these operating conditions is crucial to achieving maximum pollutant removal efficiency, while minimizing cost and potential side effects. Generation of sludge and byproducts. While phenton oxidation can reduce sludge production compared to biological processes, as what we saw a while ago, it still generates some iron containing sludge and potentially toxic intermediates or byproducts. Proper handling and disposing of generated sludge and byproducts are then very essential to prevent environmental impact. After all, why are we treating all this? We are treating the effluent for reducing the environmental impact. So, we should not dose the environment again back with some byproducts which are equally hazardous. Cost consideration. The cost of chemicals, particularly hydrogen peroxide and ferrous sulfate, can be significant for large scale applications of phenton oxidation. Cost effective strategies such as process optimization and recycling of reactants should be explored to minimize overall treatment costs. Safety concern. hydrogen peroxide and ferrous ions are reactive and potentially hazardous chemicals. Proper safety measures, including appropriate handling, storage and waste management practices, should be implemented to ensure the safe operation of phenton oxidation processes. So, there are cost consideration, there are safety concerns which need to be addressed, because it is not a foolproof process. Phenton oxidation is very good because it can be run on batch and continuous scale, it is very fast, but then there are some drawbacks. In summary, we can say phenton oxidation is a compromising technology and it is a promising technology as well for the treatment of textile effluents, offering efficient degradation of organic pollutants and color removal. However, careful optimization and consideration of operation parameters, cost implications and safety aspects are essential for its successful implementation in industrial wastewater treatment facilities. Membrane bioreactors, how are they used for textile effluent treatment? Membrane bioreactors, MBR, are advanced wastewater treatment system that integrate biological treatment processes with membrane filtration. In the context of textile effluent treatment, MBRs offer several advantages and applications. Efficient removal of organic pollutants. Textile effluent typically contain high concentrations of organic pollutants, including dyes, solvents and other chemicals. MBRs provide an effective means of biologically degrading these organic compounds using microorganisms while retaining the biomass within the reactor through membrane filtration. This results in high removal efficiencies of the organic pollutant. So, it has very good quality that it is efficiently removing the organic pollutants which are the main load of the textile effluent, and they can take care of the dyes, solvents and other chemicals. Color removal. Dyes are a major component of textile effluent and can pose aesthetic and environmental challenges in receiving water bodies. MBRs coupled with biological treatment processes can effectively remove color from textile effluent by degrading and metabolizing the dye molecules. Sludge retention. MBRs maintain a high concentration of biomass within the bioreactors due to the retention of microorganisms by the membrane. This allows for a longer solid retention time SRT, which promotes the growth of specialized microbial communities capable of degrading complex organic compounds present in the textile effluent. So, they have a very good quality that because it is retained in the bioreactor for a longer period of time, the solid retention time SRT is long, and therefore, growth of specialized microbial colonies are able to degrade these complex organic compounds in a better manner which are present in the textile effluent. Compact footprint. MBR have a smaller footprint compared to the conventional activated sludge system because they eliminate the need for secondary clarifiers. This compact design is advantageous for textile industry with limited space for wastewater treatment facilities. So, because of the compact design, they are able to contain the whole system in a very compact manner, and there is no need for secondary clarifiers as what is actually required in the activated sludge system. Flexibility and scalability. MBR systems are highly flexible and can be easily scaled up or down to accommodate fluctuations in the wastewater flow and composition in the textile manufacturing processes. This scalability makes MBR suitable for both small scale and large scale textile wastewater treatment plants. High quality effluent. The membrane filtration component of MBRs provides a physical barrier that effectively removes suspended solids, colloidal particles and microorganisms from the treated effluent. This results in high quality effluent that meets stringent discharge standards and can be reused for non-potable purposes within the textile manufacturing processes. So, it gives out treated high quality effluent. Resilience to toxic shock loads. Textile effluents may contain fluctuating concentrations of toxic substances due to variations in production processes or accidental spills. MBRs offer resilience to shock loads by providing a stable environment for microbial communities to adapt and recover from sudden changes in wastewater composition, which was not the case in the activated sludge. So, they can actually control even if there are shock loads suddenly coming into the treatment of MBR chamber reactors. They are able to keep the microorganism intact and alive. Resource recovery opportunities. MBR system can facilitate the recovery of valuable resources such as nutrients, nitrogen and phosphorus from textile effluent through appropriate process configuration and post-treatment strategies. These recovery resources can be reused within the textile industry or sold as byproducts contributing to sustainability and circular economy principles. Use of membrane bioreactors overall are versatile, effective solution for the treatment of textile effluent, offering high removal efficiency for organic pollutants, colors and suspended solid, as well as opportunities for resource recovery and water reuse. Their compact design, scalability and resilience make them well suited for meeting the stringent environmental regulations and sustainability goals for the textile industry. So, they are very well suited for the present day situation. Why? Because they are very compact. In many mills there is space constraint, and there these can be erected and they can be operated very easily. Moving on to the use of photocatalysis for textile effluent. Photocatalysis, we had learned the name and its functioning in one of the lectures earlier, but we will now see it in more elaborate form. Photocatalysis is an advanced oxidation process AOP that utilizes photocatalysts, as the name suggests. Typically, semiconducting materials like titanium dioxide or zinc oxide to generate highly reactive species such as hydroxyl radicals. So, here there is a commonality. Just like in sonochemical reactors also hydroxyl radicals were generated. In earlier cases also we saw that how in Fenton also the hydroxyl radicals are the most reactive species and most reactive oxidant, I should say, for breaking down the organic pollutants. Under the ultraviolet or visible light irradiation. In the context of textile effluent treatment, photocatalysis offers several advantages and application. Degradation of organic pollutants. Textile effluent contain various organic pollutants including dyes, solvents and surfactant, which are challenging to remove using conventional treatment methods. Obviously, if we are talking about advanced methods, this is definitely not easy to remove by the conventional methods. Photocatalysis can effectively degrade these organic compounds into simpler and less harmful byproducts through oxidative reactions initiated by photocatalytic activation. Color removal. Dyes are a major component of textile effluent. By now you must have by hearted this, that dyes, because we are talking about textile effluent and no garment is made without dyeing or printing. So, and to impart intense color, the textile effluent carries a lot of color to the water bodies, leading to aesthetic and environmental concern. Photocatalysis can break down dye molecules into smaller colorless fragments, resulting in the decolorization of textile effluents and improving water quality. Minimization of chemical usage. Unlike some chemical oxidation processes, photocatalysis does not require the addition of chemical oxidants such as hydrogen peroxide or ozone, reducing the overall chemical consumption and operational cost of the textile effluent treatment. So, since it uses very minimal amount of chemicals, this process is very cost effective. Broad spectrum of activity. Photocatalysis is effective over a broad spectrum of organic pollutants and can target a wide range of compounds present in textile effluents, including persistent and recalcitrant pollutants that are resistant to conventional treatment methods. So, you see that this is definitely an advantageous method, because what conventional methods cannot do, this method of photocatalysis, which requires less chemicals, is cost effective, can do. Environmental compatibility. Photocatalysis is a green and environmentally friendly treatment technology, since it relies on natural sunlight or even sometimes artificial light sources for activation and does not produce harmful byproducts or residues that may impact the environment. Versatility. Photocatalysis can be implemented in various reactor configuration, including batch reactors, continuous flow reactors and immobilized photocatalyst system, allowing for flexible and adaptable treatment strategies based on the specific requirement of textile effluent treatment plants. So, it is equally versatile. Synergy with other treatment processes. Photocatalysis can be integrated with other treatment processes such as biological treatment or membrane filtration to enhance overall treatment efficiency and achieve synergistic effect in the removal of organic pollutants and color from the textile effluent. So, as I told you earlier also, sometimes one type of treatment does not work effectively. One need to do 2 or 3 methods combined, and photocatalysis is one such method which can be synchronized with other methods, and the overall effectivity of the treatment is far more than what it is achieved by one single method. So, the synergistic effect of the removal of organic pollutants and color from the textile effluent is achieved in maximum quantity. So, definitely it has an edge over other methods and is very versatile and can be synergized with other methods. Long term stability and reusability. Photocatalysts such as titanium dioxide are stable and can be regenerated and reused multiple times without significant loss of activity, catalytic activity, providing long term and sustainable solution for textile effluent treatment. So, here first it is not generating any sludge, secondly or very minimal sludge, and the chemical that is used can be reused, recycled with the same effectivity, but just by regeneration. Despite these advantages, there are some challenges and considerations associated with the application of photocatalysis for textile effluent treatment, including the need of UV or visible light sources, optimization of photocatalyst properties and reactor design, and management of catalyst recovery and separation. Overall, photocatalysis represents a promising technology for the sustainable and efficient treatment of textile effluent, offering opportunities for improved water quality, reduced environmental impact and resource recovery. Now, let us see the use of activated carbon adsorption. Activated carbon adsorption is a widely used and effective method for treating textile effluent due to its ability to remove various pollutants including dyes, organic compounds and other contaminants. Here is how activated carbon adsorption is utilized in textile effluent treatment. Removal of organic compounds. Textile effluent contain a wide range of organic compounds such as dyes, solvent and surfactants, which can be effectively adsorbed onto the surface of activated carbon. The porous structure of activated carbon provides a large surface area for adsorption, allowing it to capture and retain the organic molecules from the effluent. So, not only it has porous, which is very well suited for adsorption, this porosity can retain these adsorbed material within itself. It does not exude out. So, it is very good and appropriate for removal of organic compounds, because the molecular size of these organic pollutants suits the size of the pores of this activated carbon. Color removal. Dyes are one of the major pollutants in the textile effluent and can impart intense color to water bodies, posing aesthetic and environmental concern. And time and again, whenever we talk about dyes and the color of the dye, we talk about this. Activated carbon adsorption is effective in removing colorants by adsorbing dye molecules onto its surface, resulting in the decolorization of the effluent. Adsorption of odorous compound. Sometimes the textile effluents are very foul smelling. So, they are because of certain bacteria, and pathogenic bacteria could be also present there. Textile effluent may contain odorous compound resulting from the degradation of organic matter during manufacturing processes. Activated carbon can absorb these odorous compounds, reducing the unpleasant smell of the effluent and improving its quality. Removal of trace contaminants. In addition to organic pollutants, textile effluent may contain trace contaminants such as heavy metals, pesticides and pharmaceuticals. Activated carbon adsorption can capture these contaminants through physical adsorption, reducing their concentration in the effluent to below regulatory limits. Regeneration and reuse. Activated carbon can be regenerated through thermal or chemical processes, allowing for its reuse multiple times before replacement is necessary. This makes activated carbon adsorption a cost-effective and sustainable treatment option for textile effluent treatment plants. So, you see, just like the photocatalyst titanium dioxide which can be regenerated and reused, here also the activated carbon can be regenerated either by thermal method or by chemical method, and it can be reused several times. Compatibility with existing treatment processes. Activated carbon adsorption can be easily integrated into existing treatment processes such as coagulation, flocculation and biological treatment to enhance overall treatment efficiency. So, that means it is compatible with conventional methods as well. It can also serve as a polishing step to remove remaining contaminants after primary treatment processes. Treatment of spent dye bath. Activated carbon adsorption is particularly useful for treating spent dye baths generated during the dyeing process in textile industries. By absorbing excess dye molecules from the dye baths, activated carbon helps to reduce dye consumption, minimize dye bath generation, wastewater generation and improving dyeing process efficiency. So, by absorbing excess dye molecules from the dye bath, activated carbon helps to reduce the dye consumption, so that it does not run into the wastewater. So, there it minimizes the wastewater generation and improve dyeing process efficiency. Selection of adsorbent type and particle size. This is very important. Different types of activated carbon, that is powdered activated carbon, granular activated carbon and particle sized, can be selected based on the specific characteristic of the textile effluent and treatment requirements. This allows for customized treatment solution tailored to need of individual textile manufacturing facilities. Overall, activated carbon adsorption is a versatile and reliable method for treating textile effluent, offering efficient removal of organic pollutants, colorants, odorous compounds and trace contaminants. Its compatibility with existing treatment processes, cost effectiveness and ability to regenerate make it a preferred choice for textile wastewater treatment plants, aiming to achieve regulatory compliance and environmental sustainability. So, you see, it has such broad range of activity. It can help in not only removing organic pollutants, colorants, but also odorous compound and trace contaminants. Therefore, activated carbon is very good choice for textile effluent treatment. Now, how does electrocoagulation help in textile effluent? Electrocoagulation or EC is an electrochemical water treatment process that involves the destabilization and removal of contaminants from water through the generation of coagulant species by an electric current. In the context of textile effluent treatment, EC offers several advantages and applications. Removal of suspended solid. Textile effluent often contain suspended solids such as fibers, lint and particulate matter, which can be effectively removed by EC. The application of electric current induces the formation of coagulant species, metal hydroxides, that neutralize the surface charges of the suspended particles, causing them to agglomerate and settle out of the water. So, EC can help, electrocoagulation can help all the suspended particles to settle down. Water, and so it can settle down in the water. Color removal. Dyes are a significant component of textile effluent and can impart intense color to water bodies, posing aesthetic and environmental concern. EC, that is electrocoagulation method, can effectively remove color from the textile effluent by destabilizing and precipitating dye molecules through electrochemical reaction, resulting in the decolorization of the effluent. Degradation of organic compounds. EC can facilitate the degradation of organic pollutants present in textile effluent through indirect oxidation processes. Electrochemically generated species such as hydroxyl ions and chlorine radicals can react with organic molecules, leading to their degradation into simpler and less harmful byproducts. So, hydroxyl radical and chlorine radical are responsible for the degradation of organic compounds. Metal ion removal. Textile effluents may contain metal ions such as chromium, copper, zinc, cadmium, which are used in dyeing and finishing processes. Electrocoagulation can effectively remove these metal ions through electrochemical reaction that results in their precipitation as hydroxides or oxide compounds, facilitating their separation from the effluent. pH adjustment. EC can be used to adjust the pH of the textile effluent, which may be acidic or alkaline due to the presence of acidic or basic dyeing agents. By controlling the polarity and duration of the electric current, EC can promote the formation of acidic and alkaline coagulating species, allowing for pH neutralization and stabilization of the effluent. So, even pH adjustments can be done through electrocoagulation. Sludge reduction. Compared to the conventional chemical coagulation method, EC typically produces less sludge due to the electrochemical generation of coagulant species in situ. This reduces the volume of the sludge generated and minimizes disposal cost associated with sludge handling and treatment. In one of the lectures where we were talking about sludge disposal, we saw that methods which generate less sludge are preferred, and the same thing is applicable for electrocoagulation because it generates less sludge than the typical conventional traditional coagulation flocculation method. Energy efficiency. EC system can be designed to operate at low voltages and currents, resulting in low energy consumption compared to other electrochemical processes. This makes EC a relatively energy efficient option for textile effluent treatment, especially when renewable energy sources are utilized. Compact design and scalability. EC systems can be designed in compact configuration, making them suitable for installation in space-constrained textile manufacturing facilities. Additionally, EC systems can be easily scaled up or down to accommodate variation in wastewater flow rates and contaminant loads. Automation and control. EC systems can be equipped with automated control system that monitor key operating parameters such as current density, pH and conductivity in real time. This allows for precise control of the treatment process and optimization of performance. Overall, electrocoagulation is a versatile and effective water treatment technology for addressing the complex and diverse pollutant composition of the textile effluents. Its ability to remove suspended solids, color, organic compounds and metal ions, coupled with its energy efficiency and scalability, makes it a valuable option for textile wastewater treatment plants, aiming to achieve regulatory compliance and environmental sustainability. Use of forward osmosis for textile effluent. This we did not do in much detail, only in the last lecture I had mentioned about forward osmosis. Let us see what all it can perform. Forward osmosis is an emerging membrane based separation process that utilizes a semi-permeable membrane to separate water from dissolved solutes by osmotic pressure gradients. In the context of textile effluent treatment, FO offers several potential advantages and applications. Concentration of pollutants. Textile effluent often contain high concentration of dissolved solids, organic compounds and dyes. Forward osmosis can be utilized to concentrate these pollutants by drawing water through the semi-permeable membrane, leaving behind a more concentrated retentate stream containing the contaminants. This concentrated stream can then be subjected to further treatment or disposal, reducing the volume of the wastewater requiring treatment. So, it can concentrate the pollutants and can reject that as a retentate stream, and then that retentate stream can be separated from the main wastewater, and then it will require less amount of treatment. Water recovery. Textile manufacturing processes consume significant amounts of water, and effluent treatment can generate large volumes of wastewater. FO offers the possibility of recovering clean water from the textile effluent by selectively separating water molecules from dissolved contaminants. The recovered water can be reused within the manufacturing process, thus reducing the need for fresh water consumption and wastewater discharge. Selective separation. FO membranes can be engineered to exhibit selective permeability towards specific ions or contaminants present in the textile effluent. This selectivity allows for the targeted removal of particular pollutants while retaining valuable components or nutrients in the treated water stream, enabling resource recovery and minimizing environmental impact. So, it can be engineered and designed in such a manner that one type of pollutant only can be removed at a time, and the useful components which could be nutrients in the water stream could be retained. Low energy requirement. FO operates using osmotic pressure differential, which requires minimal energy input compared to other membrane processes such as RO, reverse osmosis. This makes FO a potentially energy efficient option for textile effluent treatment, particularly when coupled with renewable energy sources or waste heat recovery system. Compatibility with high salinity effluent. Some textile effluent may have elevated salinity levels due to the use of salt based dyeing agents or other chemicals. FO membranes are generally less susceptible to fouling by dissolved salts compared to RO membranes, making FO a suitable option compatible with high salinity effluent. Some textile effluents may have elevated salinity levels due to the use of salt based dyeing agents or other chemicals. FO membranes are generally less susceptible to fouling by dissolved salt compared to RO membranes, making FO a suitable option for treating high salinity textile effluents without extensive pre-treatment. Integrating with other processes. FO can be integrated with other treatment processes such as membrane bioreactors (MBRs) or advanced oxidation processes AOPs to enhance overall treatment efficiency and achieve specific treatment objective. For example, FO can be used as a treatment step to concentrate pollutants before subjecting to retentate to further treatment processes. So, there is a possibility that FO can be again synchronized with other methods like MBR and AOPs, and that would make the process even more efficient. Flexibility in system design. FO system can be designed in various configuration, that means it can be in batch, semi-batch or continuous flow setup to accommodate different wastewater characteristic and treatment requirements. This flexibility allows for the customization of FO systems based on the specific need of the textile effluent treatment plants. So, the FO system seems to be more versatile, and because of its configuration change, one can make it into a batch or a semi batch or continuous flow system. It is better than many other treatment systems. Reduced chemical usage. Unlike some chemical treatment methods, FO does not require the addition of chemical reagents for pollutant removal, reducing the consumption of chemicals and minimizing chemical handling and disposal cost. Despite these potential advantages, it is important to note that FO technology is still at the very early stages of development and deployment for textile effluent treatment plants. Challenges such as membrane fouling, scalability and membrane durability need to be addressed to realize the full potential of FO. In this application, research and development efforts are going on to overcome these challenges and optimize FO processes for efficient and sustainable textile effluent treatment. So, it is fairly a new research that has been brought into the textile domain, that FO is still picking up, has not been one of the most established procedures for textile effluent treatment, but nevertheless it is very promising. Use of sonochemical treatment of textile effluent. Sonochemical treatment are known as ultrasound assisted treatment, involves the use of high frequency sound waves, that is ultrasound, to induce chemical and physical changes in the aqueous solution. In the context of textile effluent treatment, sonochemical treatment offers several potential benefits and application, and this is also one of the applications which was not discussed in details in the earlier lecture. Degradation of organic pollutants. Textile effluent contains various organic pollutants including dyes, solvents and surfactants, which can be challenging to remove using conventional treatment methods. Sonochemical treatment generates highly reactive hydroxyl radicals OH dot and other reactive species through the process of acoustic cavitation. These radicals are effectively degrading the organic pollutants into simpler and less harmful byproducts. Color removal. Dyes are a major component of textile effluent and can impart intense color to water bodies, posing aesthetic and environmental concern. And this we have seen time and again. Whenever we talk about color removal, we talk about this. Sonochemical treatment can break down dye molecules through oxidative reaction induced by the ultrasound, leading to the decolorization of the effluent. Enhanced mass transfer. The acoustic cavitation phenomena induced by the ultrasound creates microbubbles and localize high temperatures and pressures within the solution, resulting in enhanced mass transfer processes. This facilitates the diffusion of the pollutants from the bulk solution to the surface of the catalyst particles or membranes, thereby improving the treatment efficiency. Disruption of the cell structure. Sonochemical treatment can disrupt the cell structures of the microorganism present in the textile effluent, leading to cell lysis and inactivation. This can help reduce the microbial load in the effluent and mitigate the risk of microbial contamination in the receiving water bodies. Minimization of chemical usage. Sonochemical treatment does not require chemical reagents for pollutant removal, reducing the consumption of chemicals and minimizing chemical handling and disposal or cost. This makes it potentially cost effective and environmentally friendly treatment process. Selective degradation. Sonochemical treatment for textile effluent can have selective degradation. And it is tailored to selectively target specific pollutants or contaminants present in the textile effluent by adjusting the process parameters such as ultrasound frequency, power density and treatment duration. Compatibility with other processes. Sonochemical treatment can be integrated with other treatment processes such as AOS, biological treatment and membrane filtration to enhance overall treatment efficiency. Energy efficiency. Sonochemical treatment system can be designed to operate at relatively low energy consumption levels compared to other treatment technologies. This makes them potentially energy efficient option for textile effluent treatment. While sonochemical treatment shows promise for textile effluent treatment, it is essential to consider factors such as equipment cost, scalability and operational parameters optimization to ensure effective and sustainable implementation. So, to summarize, in conclusion, we can say that advanced technologies, treatment technologies offer innovative and effective solution for addressing complex challenges posed by the textile effluent. And in conclusion, FO selectively separates water from dissolved solutes. Some new technologies we have discussed, that is FO and sonochemical, which can help reduce the pollution load by efficient treatment methods. Continued research, development and implementation efforts are essential for further enhancement of the performance and feasibility of these advanced treatment technologies for textile effluent treatment. So, with this we have come to an end of this lecture. Thank you.